Okay, we're going to continue on here. Chapter 17. Why not go with that? So we've been talking, obviously, in this chapter last time, some electrochemistry. We talked about, felt longer to write than I thought. We talked about at the beginning, we went over some examples of balancing our redox reactions, again, in acidic and basic solutions. So remember, that is especially the sort of water method, if you will, where we use water to balance out our oxygens. We need to add some H pluses, add some electrons, add everybody back together along the way. As we talked about, it's really important, especially in this sort of chapter, and anytime you're dealing with sort of redox reactions, again, to be able to correctly identify sort of what is being oxidized and what is being reduced, and what, say, your oxidizing agent, your reducing agent. Again, we can look, as we talked about, at the oxidation states of what we're comparing from, again, the left-hand side of the arrow to the right-hand side of the arrow. And as we've talked about, if something, again, loses electrons, it is going to become more positive. And if it is moving in sort of this direction towards the positive side, again, that's substance that's going through oxidation. If you're following the oxidation state of a species there from the left to the right, and it's kind of moving in this direction, kind of in the negative direction, that means it's probably gaining some electrons and it's going to be reduced or going through reduction. Again, our oxidizing agent is a substance that gets reduced, and our reducing agent is the substance that gets oxidized. Again, they're called that, as we talked about, because they basically cause that sort of effect in the other substance. So in order for, again, somebody to be reduced, they pretty much need to have somebody lose electrons. So they cause somebody to lose those electrons, and is why they're known as the oxidizing agent. For somebody to be oxidized, that means they're obviously going to lose electrons, and by default, somebody will have to pick up those electrons, and that's going to cause the reduction, obviously, in the other substance. Once again, usually on the left-hand side of the arrow there, the reactant side is where we find our reducing agents and oxidizing agents. And we got into really sort of the heart of the chapter, which is our friend, the galvanic cell. And the galvanic cell is really a redox reaction that takes place where we sort of use the sort of flow of electrons to do some type of work. So there's really a couple of parts to a galvanic cell. We have one beaker, which is the anode side. We oftentimes, in a traditional one, will have a beaker that is the cathode side. And again, we will usually have some type of solid electrode that represents a metal. And for example, if this was, say, zinc, we would then have a solution on our anode side that has zinc ions in it. Maybe like zinc sulfate, maybe, I think, is what we might have looked at, or any type of thing, or zinc nitrate. The anode side is connected through a wire. Oftentimes it'll go through a voltage meter to the other side, where we also will have sort of a metal electrode. And for example, if this was, say, copper over here, and we would then have a solution that contained copper ions floating around in it. And again, something like copper 2 sulfate would do the job. Now, the anode side is the side where oxidation occurs. So this is the side where they will lose electrons. So electrons would travel through the wire here to the other side. And in the cathode side of our galvanic cell, that is where reduction will take place. And there's also another really important thing that sort of connects both of these things and really sort of completes the whole circuitry of here, if you will. And that is the salt bridge. And a salt bridge can be a tube that has something like cotton at the bottom there. And usually our salt bridge is filled with some type of electrolyte solution, some type of strong electrolyte solution that breaks apart. So I think maybe we looked at potassium chloride being in there as an example. It could be like sodium nitrate if you like, or any really sort of electrolyte type solution. And this allows really those electrons to sort of flow from one side to the next. What's ultimately happening here is our zinc that's in the solid state on the electrode here, they are going to lose electrons. And when they do lose electrons, they're going to go for a swim here, basically. And they're going to make zinc ions into this solution. And those electrons that will transfer over here will then kind of hook up with the copper ions that are in the solution. And they will then get reduced and they will actually get out of the pool, as we talked about, and kind of plate themselves there onto the solid. So we have sort of this electron being transferred. As the electron is transferred from one side to the next, it can be used to do some type of work. And it's pretty much what a battery is. Again, as it goes through, say, your compartment, it could power something like a light, a motor, or something like that, and then goes to the other side. And this is the process that happens. You could kind of think of it that there is a potential difference between the cathode and the anode. You kind of think of it as more positive over here, sort of happening. And that sort of positive charge there on the cathode is what essentially will kind of pull those electrons from the anode side to the cathode side. And that is why, as well, that the salt bridge here is really important, as we talked about. If we send our sort of guys this way and this way here, those ions are going to enter the solution. It's going to prevent really the cell from sort of not working and stopping. And as we talked about last time, it really prevents the buildup of charge that you would get that would sort of cease the flow of electrons if you didn't have that additional electrolyte solution in the salt bridge. So if we again took out our salt bridge here, and if we took out the salt bridge and we ran this cell, even get my cotton out of the thing. What's going to ultimately happen here is all these zinc ions are going to be made as this oxidation continues. So what's going to happen is we're going to have a lot of zinc ions in that solution, and we're going to build up a really big positive charge from all those zinc ions that are going through oxidation. Same thing over here. What's going to happen on the right-hand side and the cathode side is as those electrons go, we're essentially getting rid of all the positive charge that's sort of over there on the right-hand side. And that's going to leave us really like our sulfate here kind of left over. And we're going to build up this kind of negative charge that's going to happen there on the cathode side. And that's really bad since we want to transfer our negatively charged electrons to the other side. Very quickly, what's going to happen because of this buildup of negative charge here, negative electrons and negative side, they are not going to want to go to each other. And why would they leave? As I mentioned, I think last time, you have this big old giant positive charge over here on your anode side. So that's basically going to cease the flow of electrons. So the salt bridge is really vital to keep the charges, or sort of the correct charge balance, if you will, in place and not allow the wrong charge to build up, which is what would happen if you sort of take the salt bridge out. By having that salt bridge in there, that allows this buildup here of negative charge, say on this side, and positive charge on this side to basically not happen. So because of that salt bridge, we could send like our potassium ions this way to combat that negative charge. We could send our chloride ions this way to combat that positive buildup. And again, it allows it to sort of complete the circuit and keep everything flowing the way that it should. Now, we talked about that we could actually calculate the cell voltage, which is sometimes referred to as the EMF, the cell potential. You're asked any of those things, they pretty much want you to calculate the cell voltage. And we could use this equation here, which is E of the cell is equal to E of the cathode minus E of the anode. And remember, as we talked about this, if you are going to use this equation, which is perfectly fine to use this equation, our formula, you want to make sure that when you go to the SRP table, which stands for standard reduction potential table, remember that because they are all reduction potentials, they are all written as reduction reactions. And the purpose of the minus in this equation is it will actually change the sign for your anode, which is the one that you actually do need to flip. And if you don't want to worry about sort of flipping the equation and you can identify cathode and anode, you could go right into there, subtract the two values, and that minus will change the sign for you. If you want to change the sign, which is basically what you would always have to do when you go to that table and find the anode reaction, you would have to flip it around. And remember, when you flip one of those SRP sort of reactions, the sign changes. So if it was positive, it become negative. If it was negative, it become positive. You should then add them together. So if you want to subtract, you should not change the sign. So do not change the sign. If you want to change the sign, which is technically correct if you do write the anode half reaction, you should add them together. So if you want to add, you should change the sign yourself for your anode. And again, I don't personally care which one you do, but I would probably maybe pick one way and just kind of stick with it so you don't find yourself sort of changing the sign and then subtracting and putting it back to where it shouldn't be and stuff like that. Remember, though, that if you are writing and sort of giving an SRP value or a SOP value, a standard oxidation potential value, you should give it for how the reaction is written. So if we had, say, something like this, 2A plus an electron, actually, we'll just do that. A for electron goes to A minus, and our E naught is minus 4 volts. And we have B plus an electron goes to B minus, and our E value here is 2 volts. Remember that the other thing that we talked about was if you are building a galvanic cell and they really do not give you any information about how the reaction is happening or don't give you an overall reaction, the way you can decide which one should be your anode and which one should be your cathode is the one with the SRP value that is more positive should be your cathode. So if we weren't given any other information other than we built a cell with A and B, we would actually choose this one as our cathode because it's more positive. And by default, that would mean that this one would be our anode. So again, if we were going to write the correct anode reaction, we would flip this around. And what we would do with our E value is it would become positive 4 volts in this case. And again, this is how you should write the E value for that reaction written like that as an oxidation reaction. You should give it sort of the correct sort of value or sign if you are quoting it. Now, if I did that and we're going to get the E of the cell in this case, I would take the 4 plus the 2 in this case because I already changed the value. And that would give me 6 volts. If I don't want to worry about that because I know this is my anode, I would take 2 minus 4, and that would turn that into a positive 4, and it would get the same 6 volts. So again, if you don't want to worry about it, which sometimes you don't, because maybe sometimes you're just asked, what is the cell voltage, and you just want to figure out the cathode anode, you go to the table and don't have to worry about flipping signs. You could just plop it into that one with the minus and it'll change it for you. But again, if you want to put the sign, just make sure you add. And if you don't, then obviously don't change the sign and subtract. Any questions on any of that there? All right. So I think we left off somewhere around here. So cell potential, electrical work, and free energy. So we're going to relate our cell voltage here, which is our E, to our free energy, which we remember from the previous chapter, our delta G. And remember, free energy, there's some energy to do some type of work. So the work that can be accomplished when electrons are transferred through a wire does depend on sort of the pull or the push behind those electrons. And the EMF difference is a volt, and a volt is basically equal to a joule over a coulomb. Again, a joule is a unit of energy. Coulomb is an energy of charge. So 1 joule of work is produced are required when 1 coulomb of charge is transferred between 2 points where you have 1 volt sort of happening. And when a cell produces current, the cell potential is positive, and that current can be used to do some type of work. So essentially, when you do calculate a cell voltage and you get a positive voltage, that's really good because that will allow it to do some type of work. If you don't do that and you end up with a negative voltage, you don't get so much work kind of happening there. So an analogy, I guess, would be if you put your batteries in backwards, it doesn't work so well, right? Because you got your anode and your cathode switched around. So if you switch your batteries around in the right orientation, you get some redox reaction happening, a galvanic cell sort of happening, and you get some work sort of working in that situation. So ultimately here, the maximum amount of work that can be done would be equal to Gibbs free energy, or the change in free energy. So there has to be obviously a relationship between those two, and let's talk about the relationship between our E of our cell and our thermodynamic sort of values. I'll pop all these up here and then we'll talk about everything that's here. All right, so the first really important equation is sort of this one here, or the top one, whichever one you like. That's our delta G, and that is our Gibbs free energy. That is negative. N is the number of moles of electrons that are in a particular reaction. F is Faraday's constant, and it is a constant. We'll use the rounded number here, 96,500. It's like 96,486 if you want sort of the full number there. And that is a joule volt per mole. And remember that a joule over a volt is actually equal to a coulomb. So sometimes a coulomb over a mole is sometimes used. And our E of the cell here is the same one that we've been talking about. So that's going to be our cathode minus our anode. Again, if you don't flip the sign, just like we did before. So this one allows us to figure out the Gibbs free energy. A reminder that if we do calculate delta G and it is a negative value, it is a spontaneous reaction. And obviously, if we calculate delta G and it is a positive value, it's a non-spontaneous reaction that's going to occur. Now, really important here when you do use this equation, and that is the N, and sometimes people do how to say this, mess up on the end, if you will. So if we look at two fakey half reactions here, I guess we'll do this. 2 plus 2 electrons, and 2 electrons plus a I'll be 2 gives us B in this case. So these are, say, our 2 half reactions going here, and I think I wrote them right. We got our oxidation half reaction over here, and we have our reduction half reaction over here. So if we needed to use N in this case is actually equal to 2. It is not 4, so you don't add those together or anything like that. And the idea there is obviously the amount of electrons that the guy being oxidized loses is the same amount of electrons that the guy being reduced gains. So what we're looking here is really the electrons that are being transferred. So you do need to make sure they're balanced. So obviously if you had like 3 in one and 2 in the other, common number there would be 6. So N in that case, and the balanced equation would be 6. So you want to make sure you don't add them together, but you do need to still make sure that they are balanced so that you get the correct number of electrons. Now, if we look at our friend equilibrium constant, and if we have some type of situation that involves the equilibrium constant, because we couldn't go too far without K here, we can actually calculate E of the cell using the equilibrium constant. This is RT and F. This R is the gas constant, but again, it is the one that involves energy, so it is the 8.314 version of it. T is our temperature in Kelvin. N is still our moles of electrons, and F is still our Faraday's constant, which is up here, whichever one you want to use there. And natural log of K, K is still the equilibrium constant, so it's still products over reactants, exponents, the coefficients, just like you normally would calculate K. So if you have some type of question that involves the equilibrium constant, either you're trying to find it or you're given the equilibrium constant, you want to figure out about something like a galvanic cell, obviously the second one is the one that you would use. The first one is very helpful just to use to figure out whether or not, for example, a reaction is going to be spontaneous, and also figure out how much free energy you could use. We could actually figure out if the reaction will be spontaneous just by the E values. Now, there's two other versions of this equation, and that is what these are right here. And these are the sort of simplified versions of these equations at 25 degrees Celsius, because at 25 degrees Celsius, basically the temperature, the R and the F all become constants, basically. And if you want to do it, you could do 0.0257 volts divided by N, natural log of K. Or if you're more of a traditional base log 10 of situation here, 0.0592 volts divided by N, regular log there of K. So those are two versions of the equation here where we sort of simplify things down. If you don't want to worry about these equations, you absolutely do not need to. You could frankly just plug and chug into that equation and it'll come out pretty close to the same. I will say that there will be probably some variations depending on which version that you use of that equation and where you round, especially in a situation if you're going to solve for K and you do a little bit of rounding and stuff like that. You might get a slightly different front part of the number. Exponent part usually will be right on, but the front part might be a little bit off again, especially in a lot of cases if you're kind of solving for K in these. And depending on sort of where you round, you might get a slightly different number. But again, the exponent part should be pretty close, and even the front part should be relatively close, but it might be slightly off with rounding. So anything involving the equilibrium constant and a galvanic cell and E of the cell, you want to roll probably with this equation. And obviously our delta G, you would roll with those. So those two really the most important ones out of here. The bottom two, like I said, you don't really even have to worry about those. You could just plug it into the first one. And obviously you could just go 298 and use all the constants. This is our triangle of death over here. So we got E of our cell. If we know that, we could use this equation here to get to our thermodynamic value of delta G. If we know delta G, we could get to K by using the equation we saw in the previous chapter. And clearly, if we know K, we could get to ERK going in that direction. So that's how all three of those sort of equations relate to each other here. Speaking of our equation, if we look at the one that we were just looking at, which is our delta G is equal to minus NFE. The idea here is a couple of things. If we have positive voltage here, that's why positive voltage is good, because F is a positive number, N is a positive number. That means no matter what you do, your delta G here is going to be negative, which means that reaction would be spontaneous. So that's why we're looking for positive voltage here. If you had negative voltage, that negative and the front negative will turn your delta G always into a positive number, which means it will be non-spontaneous. So that is why when you get a negative voltage, it's a non-spontaneous process. To fix that, you essentially would just swap your anode and cathode, right? So you would unclip them, clip them the other way, and then your cell would perhaps work in that kind of situation. And analysis to flipping your batteries around the right way. We also could look at obviously the one here with our K, and it works the same way. If we got some positive voltage happening, we're going to get a spontaneous reaction. And if we get a spontaneous reaction, that means that reaction should be heading to the products, and we should have more products than reactants at equilibrium, and we should have a larger value for K. Vice versa, if we got some negative voltage, that means the reaction will be non-spontaneous, which means it's pretty much going to hang out over there on the left-hand side, on the reactant side, and we would end up with more reactants than products and a lower K value. So again, all those things, should make sense with each other. Any questions on that there? All right, let's try one here. Calculate delta G for the following. Okay, so let's take a look at this. We're going to try to calculate our delta G, in this case, minus NFE, since we do have some SRP and some galvanic cell information given to us. We do have an equation here. So our cathode, in this case, we see our copper is +2, and it goes to 0 in this case, which means it is being reduced or oxidized here. It is being reduced again. It's starting at +2, ending at 0, making more negative. So it's becoming reduced. By default here, our iron's going from 0 to +2. So starting at 0, ending at +2, becoming more positive, being oxidized. So that means here our copper is our cathode, right? And our iron should be our anode in this case. Any questions on that identification? By the way, they did give us the equation, which is why I went to the equation and not just use the SRP values to make sure what is going on. In this case, you would be lucky because it actually matches, right? See which one's more positive, but again, you should look at the equation if they give you one. So in this particular case, we do need to calculate E of our cell. And in this case, I'm just going to subtract. So I'm not going to change a sign in this case. So I'm going to take the cathode, which is 0.34 volts. I'm going to minus it from our anode, which is minus 0.44 volts. That's going to give me 0.78 volts as my E of the cell, which is what I need here. Remember that F is a constant, so F is 96,500 joules per volt per mole. We do need to figure out N in this case, and we can see in this case it is balanced and N should be 2. Again, we're not going to add those guys together. So putting into our formula here, that's going to give us negative 2 moles, our 96,500 joules per volt per mole, and our voltage there of 0.78 volts. Volts will cancel, moles will cancel. This is going to leave us our delta G there in joules. That's going to be a 2 times 96.5 times a 0.78. Will give us a negative 150,540 joules, or we'll round a little bit there, maybe a minus 151 kilojoules in this case. Yeah. First off, any question on the calculation? Is this reaction spontaneous? It is spontaneous. And by the way, when we hit here, that's pretty much we know it's going to be spontaneous because we did get a positive voltage. So that should give us, again, a negative delta G, which means it is going to be spontaneous because of that. That means that we would expect in this reaction it to proceed in this direction towards our products in this case. Any questions on any of that calculation there? And remember, typically delta G is usually given in kilojoules, but it doesn't really matter. If it didn't specify, you could have left it, obviously, joules as well. All right, let's try maybe another one. The question is, will 1 molar nitric acid dissolve gold metal to form 1 molar gold 3 ions? Here's some SRP values from a table. All right, take a few moments there, see what's going to happen. Will my gold dissolve? Okay, so let's take a look. So in this case, my cathode is which one? Which one? First one. And that is correct. The top one is the first one here. That is my cathode. This is my anode. And you may be saying, hey, isn't the bottom one more positive? And you would be correct. But the question asks, Will nitric acid dissolve gold metal to form gold 3? That means gold metal by itself needs to be on that side. So that is actually the one that needs to be flipped in this case. So again, because they told you how this reaction is going to take place, bless you, that would make this one my anode and this one my cathode. So again, really important. Sometimes people just autopilot. Positive one's always going to be the cathode. You want to make sure if they do give you something like in words here, or they give you the overall reaction like the previous one, that you do look and see what's going on. So with that being said, we could calculate E of the cell correctly here by taking E of the cathode minus E of the anode. Once again, I'm subtracting, so I'm not going to change signs, but I've already identified what one is which. So we're going to take 0.96 volts minus 1.5 volts in this case. If you did flip the sign, you would be adding them together after you flip the sign, obviously. And either way that you do it, you'll end up with a negative 0.54 volts, which right there would tell us that this is going to be non-spontaneous, as we didn't really get positive voltage. And we know that from just going into the other equation, minus NFE. Here, this is going to be negative. Along with this negative, we'll then turn our delta G again into a positive, and that obviously is no good for spontaneity as well. Also, if you watch like pawn shows on TV years ago, that's how they test if you bring them gold. Like they throw nitric acid on it, and if it's still there, it's gold, right? If it's not so much there, then it's not really gold. In that case, you can learn a lot from TV sometimes, so you can learn these things. Any questions on any of that there? How come I didn't do what now? I didn't, because I chose to use the equation where you subtracted. If you wanted to switch the sign, then you should add them together. So if you wanted to correctly flip this guy around, where it would look something like this, then the E naught would be minus 1.50 volts. And at that point, you would take that one along with our first one that we did not flip, and you would add them together instead of subtract, because you changed the sign yourself, and you should get the same cell voltage there as you did there. So remember, if you use the one where you subtract, then the minus part is what flips the sign for you, so you don't have to do it. Yeah. Question? Yeah. What's that? I am minusing the anode. This is my anode, the 1.5. This guy on the bottom is the anode in this case, the gold.
I'm confused about the equation when to flip it.
So we did two flipping here for a reason. So let's talk about this question here and first. In this question, because of the way it was worded, it wanted to know if you took nitric acid and reacted with gold metal. So those are your reactants. So those are the two things that you need on the left-hand side of the arrow. And if we come down here, this is nitric acid, it's on the left. Over here, this is gold metal, it's on the right. So that's how we knew in this particular example that even though the second one had a more positive E value, that one needed to be flipped because of the way the question was being asked, that is the nitric acid going to react with the solid gold metal. Now, because of that we know that was our anode, and because it was the anode, I could just label it as the anode, and I don't have to actually flip the sign of it if I use this equation where I subtract, because that subtraction will change the sign for you. Now, the one that you always have to, if you want to flip the sign, you should always put the sign on the anode one. And if you did that, that would get you, like I wrote down here, that if you flip that one as the anode, you would change the sign, and then in that case, you should add them together. So in this particular example, we're not going by which one was more positive, would be your cathode or anode. We have to go by what the question was actually asking to figure out which one was your anode and cathode. But it's always, if you are going to flip the sign, it's always the anode one that you have to flip. And we're always subtracting the anode, and we did that in both of these cases here. Other questions? No. All right, so let's take a look at another one and see. Here's some SRP values. We want to know what is the equilibrium constant for the following reaction. So see what you come up with in this particular case. Okay, so let's take a look. So we are looking for the equilibrium constant here. So we probably should use the only equation there that has it, although we did see three of them. But you could use E of the cell is equal to that is RTNF, natural log of K in this case, I believe. And we are looking for RK. You also could use one of the other two sort of reduced down versions if you wanted to as well, since it's at 25 degrees. So we need all the other components here. So we do have R, which is a constant, and that's 8.314 joules per Kelvin per mole. We do have our temperature that does need to be converted to Kelvin. So that's going to give us a 298er. And we have F, which is Faraday's constant. We'll go with 96,500 joules per volt per mole. We also need to calculate our E of our cell, which again is going to be E of the cathode minus E of the anode. Again, unless you are going to switch the sign yourself, then again, you would add both of these together. So in this particular case, our cathode is which one? Cathode is the iron in this case is our cathode. And this is our anode. And that is because they did give us an equation here, a reaction, and we see that iron is going from +2 to 0, which means it's actually becoming more negative and going through reduction. The silver here is going from 0 to +1. It's becoming more positive. So this is again a situation where they give you the reaction. You need to actually look at it and see who's being oxidized and who is being reduced to correctly identify the anode and the cathode. Remember that you go with the more positive one in a case where they pretty much don't give you any information other than, hey, you built the galvanic cell out of these two things. And, so you could then go with the more positive one as your cathode. Yeah.
Full formula, not the substitute.
What's that?
Slide, it has like one other section. It's like a simple.
Does it? It's so those should be the values that are on the slides, right? Yeah. You should have much. Yeah. Yeah. So remember that all those equations that you'll find in that table, they're all going to be written as reduction reactions because they're standard reduction potentials. So one of them does need to be sort of flipped technically, which is the anode one. So you should go by, in this case, actually the overall reaction that they gave you in the problem, because this is specifically the reaction that we're sort of looking at in this problem, which is the overall reaction, so you can see what's going on. Much like what we saw in the previous example where they were talking about nitric acid reacted with gold metal. So that's specifically sort of what we were talking about in that reaction. So that's what we have to see, what's being oxidized and sort of what's being reduced in that case. Other questions on that? So in this case, once again, I'm not going to flip the sign. And that would mean my cathode would be minus 0.44 volts minus, and again, that minus is going to flip the sign for me for my anode. So that's what that is for. Again, if you wanted to flip your anode, that would be negative 0.80, and you would add it to negative 0.44, which obviously will give you the same answer, which in this case is minus 1.24 volts as our E of our cell. Any questions on that so far? We know right off the bat here, is this reaction spontaneous or non-spontaneous? It is non-spontaneous as we got negative voltage, right? That will lead us to a positive G. That also should tell us that when we're done calculating our equilibrium constant, should it be a large value or a small value? It should be a small value, right? And that's because it's a non-spontaneous, which means it's just going to hang out on the reactant side. You should have more reactants than products, and that should lead you to a small value of K. So again, all these things should sort of match up when you do it. Let's see if it does. Last thing that we need to figure out is N. N in this case should be 2 electrons, as our proper half reactions is iron plus a couple of electrons going to iron here with no charge, with our E being minus 0.44 volts. It is the silver that gets flipped around there. So a little silver going to 2 silvers there, plus a couple of electrons. And really, this is going to be minus 0.8 volts. So once again, this is how we get to our overall reaction. And that is where we get our N value, which is 2. And again, if you flip the sign, as you can see, I properly wrote it correctly here with the sign being changed. If you wanted the E of our cell like we just had, you would then add these together, and that would give you minus 0.44 plus minus 0.80 volts, gives you a minus 1.24 volts. So again, if you change the sign yourself, add them. If you don't want to, subtract them, and it'll change it for you. All right, now that we got all that taken care of, that basically means we got a minus 1.24 volts is equal to 8.314, which is our gas constant times our temperature in Kelvin, divided by our N, which is 2 moles, and our F, which is 96,500 joules per volt per mole. And that's going to be the natural log of K. Kelvin will cancel, moles will cancel as well, and our joules here will also sort of cancel, and our volts will cancel out as well. So we will end up with cleaning up maybe both sides, or the right side, 8.314 times 298 divided by 2 divided by 96,500. Going to give us a negative 1.24 volts equals 0.012837 natural log of K. We're going to divide that to the other side, and that'll be negative 1.24 divided by 0.01283761. That's going to give us a negative 96.595, we'll call it, equals the natural log of K. To get rid of the natural log of K, we're going to take the E of both sides there. That's going to get rid of the natural log, and that will give us a K value in this case of, call it 1.1 times 10 to the minus 42, which I would classify as being small. Now, again, as I was talking about earlier, if you chose one of the other 2 equations to reduce down one, or if you round a little bit differently than I did, I didn't really round very much at all on my calculator. Again, you might get a slightly different front number, but you should still get to the minus 42 there on the exponent. Any questions on any of that there? Yeah.
For oxidation reaction, switch it back to reduction. What's the value that you tell which is the cathode?
They might have I might have left the equation. Did I leave the equations on that one? I probably did, right? Yeah. And it has oxidation. It should have the silver as the oxidation, right? Yeah. So, and it probably has, I don't know if they changed the sign on it. Did they change it to minus 0.80 volts on that? No, they left it. Okay. So that one you would need to change if you wanted to add them. Again, if you didn't want to add them, you would subtract it with the positive value on there, and that will change the sign for you. I think where I borrowed that slide from was they only taught cathode minus anode, so they never switched the signs on any of them, but they did switch the equations to show you which one was which in that case. Yeah. Other questions on that? So again, it does boil down to, and I mentioned last time, I would again probably pick a method, either change the sign or don't change the sign, and just kind of stick with it. So either subtract or add. I wouldn't probably bounce back and forth, because again, you might kind of confuse yourself at some point and go, did I flip it, or should I subtract it, or subtract it and flip it? So choose whichever way you want to do it. Like I said, I don't care which way you do it, and stick with it. But once again, as I mentioned before, though, if you are technically going to write this reaction, regardless of what it might look like on your slide, and you're going to sort of quote the E value for it, it should really be the negative value should really be sort of displayed there as is proper for the oxidation. I know why they didn't do that in that example. It's because they do the subtraction, they don't change the signs, but you should do that. Other questions? All right, so let's then talk about the effect of concentration on the cell EMF and another really sort of important equation. And this is what is known as the Nernst equation. And we kind of get the Nernst equation from a couple of equations that we saw before. And right here is the Nernst equation. And just like we saw on the previous one there with the K, there's also sort of a reduced down version of the Nernst equation. And again, if you don't want to bother with those two on the bottom, you don't need to. You could just use the one in the box and just put the values in. So you could just pop the values into the one in the box and not have to worry about the one on the bottom. But I do put it up there because it's very common. Sometimes people will kind of use those reduced down versions of it. So you're not like, where did that come from? It does come from the one in the box and just reducing down the RT and F in that particular case at 25 degrees. So this is very similar to this delta G equation that we saw when we were doing thermodynamics, and that's where we have kind of two G's. We got two E's here, and once again, a good way to sort of think about this is the first E there is sort of under non-standard conditions. So remember that standard conditions means, as we talked about, temperature is usually 25 degrees. If you have concentrations, everybody's 1 molar. If you have pressures, everybody's 1 atmosphere. I would say probably in most cases, the thing that will be non-standard conditions will probably be the concentration or the pressures. They won't be ones, and those are very common. The E naught is your E of your cell under standard conditions. So whichever way you're going to calculate that, for example, is your cathode minus your anode in this case. The rest of it is pretty much the same deal as what we've been using. The R is, again, the gas constant at 8.314 that we just used. Temperature is still our guy in Kelvin, and is the moles of electrons. F is Faraday's constant, and a throwback Q here, which is our reaction quotient, and that is like we've always calculated Q, which is the same way you calculate K, and that would be the concentration of the products over the reactants. Again, coefficients, exponents, just like you normally would calculate it. So the Nernst equation is typically used when you have something that's under non-standard conditions. And like I said before, probably 9 times out of 10, you're going to be looking at different concentrations, different pressures maybe, or something of that nature. By the way, the Nernst equation is sort of where we get the equation that we use there for the equilibrium constant. So at equilibrium, so in case you can't remember the other equation, but know the Nernst equation, at equilibrium, E will equal 0 and Q will equal K. And that would get you 0 is E naught minus RT and F, natural log of K. Bringing this entire thing to the other side gives me E is equal to RT and F, natural log of K, which is the equation we just used in the previous problem. So good news is, if you want to remember the Nernst equation, you could derive the other equation from it by just putting those two guys equal to 0 as well. All right, so we will use this under non-standard conditions, and we could see that, you can and potentially make a sort of non-spontaneous cell reaction spontaneous, maybe by changing concentrations. You could change pressures, and that can have an effect on whether or not, you will see sort of the E of the cell get to a positive number or not. So let's take a look at one here. And I think you have these values here or not. Here's the SRP values from the table. And will the following reaction occur spontaneously? Okay, so let's take a look. So we're going to use our Nernst equation here, as we do have concentrations, and the reason we know we should use it is these guys are not 1 molar, so that is sort of the non-standard part of this deal. If it was under standard conditions, those guys would all be 1 molar, but again, they are not. So we do have a difference here, so we're going to do our E is equal to our E naught minus our RT NF, natural log of Q happening here. So we do need to figure out our E of our cell, which is our cathode minus our anode. In this case, our cathode is which one? Cathode is, it is the iron in this case. Once again, we are given the overall reaction, so we can see iron going from +2 to 0, so becoming more negative and being reduced. The cadmium here is going from 0 to +2, again, becoming more positive and being oxidized, which means the cadmium here would be our anode in that case. Any questions on that there? So we're going to take our E of our cell under standard conditions, cathode minus our anode. Once again, I'm not going to switch the sign. So I'm going to take my cathode, which is minus 0.44 volts, minus a minus 0.40 volts. And that's going to give me a whopping voltage here of something. Negative 0.04 volts. So under standard conditions, is this reaction spontaneous? The answer is no, because our cell value there is negative, which will give us a positive delta G. So under standard conditions, everybody's at 1 molar. This reaction should be non-spontaneous. So what we're going to see now is by playing with the concentrations, can we maybe get this guy some voltage here? Can we kind of turn it a little bit more spontaneous? So our R is our constant, our 8.314 joules per Kelvin per mole. Our temperature, we do need to convert into Kelvin like normal. So that's going to give us a 298. N in this case is 2. Again, we know that our iron is our cathode, which means it's going to accept 2 electrons to become this guy. And that's our cathode reaction. Our anode reaction is our cadmium will give off a couple of electrons for our anode side. And again, our N value here is going to be 2, not 4, so we're not going to add them together. F is a constant, which is 96,500. And we still also need to calculate Q in this case. Q is the concentration of our products, which in this case would be the cadmium concentration divided by our reactants, which would be the iron concentration. And like normal, right, anything that's a solid is not included, which is why you don't have any numbers for those guys, right, because they're not included. That basically is, in this case, 0.01 divided by 0.60. That gives us there 0.01 divided by 0.6 and 0.01666. We'll call it a 7 there. All right, I think we have everything we need. So plugging it in, E is going to equal our E of our cell minus 0.04 volts minus our R, 8.314, our T, 298, all divided by our moles and our 96,500. And the natural log here of however you want to do it. You can use the number or redivide it there, basically. All right, so I'm going to clean up the right-hand side of the subtract, I think. So I'm going to take point, obviously, 0.01 divided by 0.6 gives us our 0.0166. I'm going to take the natural log of it. I'm going to times it by 8.314 and times it by 298. Maybe push 298 would be helpful. There you go. I'm going to divide it by 2, which is on the bottom, and divide it by 96,500. So I basically got the number here after I natural logged it, multiplied by what's there, came back and divided by what is on the bottom. If you do all that, you'll get an E is equal to minus 0.04 volts minus a minus 0.0525598 volts. Didn't feel like rounding too much apparently. So that's going to give us minus 0.04 minus our answer. And that's going to give us here, we'll do a little rounding at this point. We'll call it 0.013 volts in this case. Yeah. Is this reaction spontaneous with these concentrations? The answer is yeah, barely, but it got some positive voltage. So we went from basically negative 0.0 volts in a standard condition. By playing with the concentrations, we were able to get it up a little bit to at least some positive voltage in this particular case. Question on that calculation. By the way, kind of works this way. Electrons will, when you play with concentration, want to always kind of move from the higher concentration to the lower in this situation. And it's a little Le Chatelier's principle as well. Since we have a higher concentration of iron, be like adding iron, it's going to cause it to move in that direction from the higher concentration to the lower concentration. And that's sort of what we saw, because it's going to want to move in that direction. The only way to do that is to become kind of spontaneous, right? And head in that direction. Under standard conditions, not going to work that way. By the way, if you did this exact same calculation and you switched the concentrations and you made cadmium 0.6 and you made iron 0.01 and kept everything else the same, would it become spontaneous in that case? It would not, because this would then be higher concentration, which means it would want to kind of move that way, and you would actually get a negative value. Just to show you, you would do that. If you did that, it's just basically flip these two around. You would take 0.6 divided by 0.01, take the natural log of it. Everything else stays the same, 8.314 times 298 divided by 2 divided by 96,500 will give you on the back end there in that situation, if you flipped it, minus 0.04 minus 0.05, and that would get you here a cell voltage of minus 0.093 volts, which obviously would not be spontaneous if we flipped it for the reason I just explained. Now this guy's higher, so the electron is next, and we want to head in the opposite direction. Any questions on that there? So you can play with concentrations. You could also do the same thing if these things were gases. Remember, some of these things could be gases, right? Have just like a platinum electrode or something like that. So you could play with pressures or gases. And you can, as you can see here, maybe take a reaction that normally under standard conditions would be non-spontaneous and get a little bit of positive voltage and make it a little bit spontaneous by playing with the concentration.